Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to discuss the common ion effect. So we're going to talk about what it is and what it will do to the molar solubility for a slightly soluble ionic salt. And then we're going to go ahead and look at the calculations involving the common ion effect, and we're going to quantify how the molar solubility is affected if a common ion is present in solution. All right, so let's go ahead and start. So when you guys are talking about the common ion effect, this is the common ion effect is nothing more than an application to Le Chatelier's principle. And so if you recall from a couple chapters ago, Le Chatelier's principle states that if a constraint such as a change in concentration, whether you increase or decrease the concentration, a change in pressure, or a change in temperature, is applied to a chemical system that's already at equilibrium, much like this chemical system that you guys see here on the screen. The chemical equilibrium will shift to counteract the effect of the disturbance or the constraint. And so once again, we're revisiting Le Chatelier's principle, but this time we're going to take it one step further and try to understand what would happen to the molar solubility of this slightly soluble, mostly insoluble salt. So we have this chemical system in solution, and it's currently in equilibrium. So we have silver chloride, and we know that most of it is going to stay as a precipitate. So we're going to see like a whole bunch of white precipitate, and however, a small fraction of it is going to decompose to produce these two ions, silver ion and chlorine and chloride ion. And so what would happen to the molar solubility of silver chloride if we place sodium chloride in the solution? Okay. So what we're trying to address is what would happen to the molar solubility of silver chloride and we're talking about the substance in which silver and chloride are together. So it's the reactant on the left side of the arrow. So what's going to happen to the molar solubility of silver chloride when we add sodium chloride to this solution? Now, if you guys recall, sodium chloride, when you guys place it in water, it's going to dissolve to produce sodium, the cation of the sodium, and chloride. And we're able to come to this conclusion using our solubility rules. So if you guys look at the solubility rules for NaCl, sodium is a group 1 ion. And once you have a group 1 ion within the chemical formula, you don't really need to check the solubility rules for its partner because group 1 ions are always soluble. And so when you place them in solution, it's going to dissociate or dissolve to produce sodium ion and chloride ion. And so we're going to go ahead and write that reaction, if you will. We're going to go ahead and write that right underneath the current equilibrium that you guys see on the screen. So you have sodium chloride that's going to dissolve to produce sodium ion and chloride ion. So I want you guys to notice that the arrow does point one way. And so it's understood that most, if not all, of the sodium chloride will dissolve to produce the sodium ion and chloride ion. Now, if you guys are looking at these two equations, you'll notice that there is a an ion that is in common between both of these chemical equations. Hence the name common ion. And so chlorides is a common ion between these two chemical equations. And if you guys are just focusing on this, first equation down at the bottom, the separation of sodium chloride's crystal to sodium ion and chloride ion will increase the concentration of the chloride ions overall in the solution. So the addition of sodium chloride will increase the concentration of the chloride ions. And so if you guys think about this with respect to Le Chatelier's principle, if you have an immediate bump in the chloride ions, to counteract this disturbance or this constraint that you added, that you applied to the chemical system that's already at equilibrium, it's going to want to counteract that effect. And so to counteract an increase in the chloride ion, overall, the equilibrium will shift such that it favors the production of the silver chloride that I'm going to go ahead and box in red. Okay. So here we have a shift in equilibrium, and it's going to shift to the left. And so if you guys want to apply what you've learned in the equilibrium chapter with respect to the seesaw technique, you can go ahead and think of your reactant, which is going to be silver chloride. It's in balance with silver ion and chloride ion. And so if you add more chloride ions, it's going to tilt this seesaw downwards to the right. Okay. And so this is the disturbance in the equilibrium. Now for this seesaw to rebalance itself, you probably need to produce more. So you need more silver chloride to rebalance this out. And the only way that's possible is if you consume some of the excess chlorides. Actually, let me draw chloride up here. So what you're going to do is you're going to consume, the excess chloride. By reacting it with the cation that's present in the solution. In this case, it's going to be silver. And so by consuming your excess chlorides, you'll be able to rebalance this seesaw, if you will, so that the chemical system can reach a new equilibrium. And yes, I did add in another silver, right? And the reason why I added another silver is because typically in a solution, you just don't have one ion. You have either a mole or a fraction of a mole or a multiple of a mole, right? Long story short, you have more than one of those substances. And so right now I just, combined silver and chloride, that's silver and the excess chloride that was added to the solution to produce more silver chloride. But you still do have, silver ion present. Its concentration is decreased due to the addition of this chloride. Okay. And so overall, there's going to be a net shift in the direction, in net shift going to the left So in other words, the equilibrium is going to favor the production of more silver chloride. So I'm just going to go ahead and put in here that the addition of the common ion, in this case it was the chloride ion, shifts the equilibrium in favor of production of silver chloride. Okay. And so what we want to, and that's great, that's what we learned when we were talking about Le Chatelier's principle, and that's pretty much the extent of Le Chatelier's principle with respect to the common ion effect. Now what we want to address, what we want to do is take it one step further and ask ourselves, how does adding a common ion affect the solubility of the slightly soluble compound? And so in this scenario, remember the common ion was chloride because you see, that's the ion that both these equations have in common. And so the slightly soluble compound that we're referring to is silver chloride. Well, since you're making more, since the equilibrium favors the production of AgCl, the forward reaction is no longer favored. So let me clarify that up. So I'm just going to go ahead and redraw this once again. So here we have AgCl. Okay. And we have Ag plus Cl minus. And I'm actually going to redraw my arrows to be a little bit more accurate with what's going on here. So remember that silver chloride is an insoluble or slightly soluble substance. Slightly soluble, mostly insoluble. And so the reason why I keep on repeating this is because if I'm depicting the arrows to represent, the equilibrium constant, the ratio of equilibrium constants with respect to each other, since silver chloride is slightly soluble and mostly insoluble, the forward reaction, the separation of the silver chloride to produce silver ion and chloride ion, is really not as favorable compared to the reverse, right? So naturally, this silver ion is going to come together with this chloride ion to produce your slightly soluble salt. But at equilibrium, there's going to be this, fine balance between the two. And so when you increase the concentration of chloride by adding sodium chloride, it pushes the arrow even further to the right, to the left, making the arrow to the right that much smaller. Okay? So in other words, the molar solubility and the forward direction is, you guys can think about it as the molar solubility. The amount of silver chloride that will be soluble is even less, since the equilibrium is favoring the production of this slightly soluble, mostly insoluble salt. Hopefully that made sense. Okay. So since the equilibrium favors the production of AgCl, the molar solubility or its ability to dissolve, just to kind of put it in layman's terms. So ability to dissolve to produce the ions decreases. Okay. And so it's all about Le Chatelier's principle and the equilibrium shifting to the left. And that's going to inform us that since more silver chloride is being produced it, to reach this new equilibrium, or in this new equilibrium, since silver chloride is produced more, then it's the ability for silver chloride to break down and produce these two ions, its molar solubility decreases. Okay. And that's basically the take-home message for the common ion effect, right? And so what we're going to do is we're going to demonstrate the common ion effect by quantifying the molar solubility. And so it gives, by looking at the actual numbers, it gives further data and proof of the common ion effect. So let's go ahead and start. So so pretend like this is an experiment. And in an experiment, you guys need a control. And so the control is a substance that doesn't change. You know that it's like this constant. Okay? And so if you guys are reading this first part A, we're going to calculate the molar solubility of strontium fluoride in water. And the KSP of strontium fluoride is 4.33 times 10 to the negative 9. So this substance in water with no addition of any ions will have a specific molar solubility at a specific temperature. Let's just say at 25 degrees Celsius. Okay? And so part A is going to be our control. Like, what is the molar solubility when we're at 25 degrees Celsius and we're not adding any common ions? And we're going to see how that molar solubility will change once we start adding common ions to it. Okay. And so to calculate the molar solubility of strontium fluoride, when it's just in water, you're just going to write the dissociation, if you will, of this slightly soluble, mostly insoluble substance, which is strontium fluoride. So strontium is Sr, and it has +2 charge. Fluoride is a negative charge. So you need two of the negative charges to balance the positives. So we have SrF2, and this is going to be our slightly soluble substance. Now, how do I know that it's solid? One, you guys can look at your solubility rules, but I don't think that there is a solubility rule for fluoride that I've placed. And typically fluorides are not listed in your solubility rules. And so the gold standard really is looking at the magnitude of the KSP. Okay? And so really the KSP is the gold standard to determine how, roughly how insoluble or slightly soluble that specific substance is. Okay. And, those solubility rules really are just there. They're kind of like the starter Lego kit, whereas KSP is like the more advanced, cool, Star Wars, let's build a whole massive Death Star scenario. And so since the KSP is time sensitive -9, then we know that this substance, strontium fluoride, is going to be our slightly soluble, mostly insoluble substance. And so since it's slightly soluble, we know that at some point in time, it's probably going to reach equilibrium. And when it reaches equilibrium, some of those ions, or some of the ionic compound, is going to dissolve to produce its ions. And so here I always want to write a balanced chemical equation, and it's based off of the ratio from the subscript. So for every 1 strontium, there's 2 fluorides. All right, so now that we have our balanced chemical equation, I'll just put a 1 here just for clarity. I'm going to go ahead and build my ice table. Real quick, we need to determine what we're calculating. We're calculating the molar solubility. And so what is the molar solubility in the ice table? It's going to be S. And so oops. All right. So in the problem, it didn't really give us an initial concentration of strontium fluoride, so we're just going to kind of leave it blank. For C, the change, we know that some of the strontium fluoride will be soluble. In other words, it's going to dissolve to produce strontium and the fluoride. And in the problem, we didn't really have an initial amount for the products either. And so at equilibrium, if you want to just put minus S, that's fine. But we know since this is solid, we're not really going to take this into account in the mass action expression. So this is plus S plus 2S. Now that we have our ice table, we're going to go ahead and write our mass action expression to relate it to that of KSP. And so the KSP is 4.33 times 10 to the negative 9. And so the strontium raised to the first times this by fluoride raised to the second. And so I forgot, so 4.33 times 10 to the negative 9. That's going to equal to S times this by parentheses 2S squared. Okay. Now, when you reduce all of this, remember that you guys are going to distribute that square to both the number and the letter. Your final outcome is going to be 4S cubed. Okay. And so that's going to equal to 4.33 times 10 to the negative 9. And so to solve for S, we're going to go ahead and take this value and divide it by 4. So I'll just go ahead and write the outcome there. So S cubed is what we'll have on the right side of the equal sign. Once I divide 4.33 times 10 to the negative 9 by 4. And here what I get is 1.08 times 10 to the negative 9. I'm not done yet. I need to get rid of this this exponent. And what I'm going to do is I'm going to cube root both sides. Another way that you guys can express that cube root in your calculator is put 1.08 times 10 to the negative 9. Raise it to the 1/3 power. And that's going to produce that's going to give us S. Okay. And so when I calculate this out, I get 1.03 times 10 to the negative 3. And so since S, if you recall from the first lecture video, S represents the molar solubility of our slightly soluble, mostly insoluble substance. So this is going to refer to the molar solubility of, what was the strontium fluoride. Okay. And to make sure that we are representing molar solubility, we're just going to go ahead and add the unit molarity. And so it turns out that if this is just in water, the molar solubility is going to be 1.03 times 10 to the negative 3 molar. Great. And so that number actually doesn't really mean anything to us. It only means something more once we start comparing it to something else. Okay. So let's go ahead and do part B. Okay. So remember that this value is our control, right? I'll just go ahead and put in control. All right, so now we're going to calculate the molar solubility of strontium fluoride in 0.25 molar of lithium fluoride. Okay. And so once again, I'm going to go ahead and write my chemical equation, strontium fluoride, to produce strontium and 2 moles of my fluoride ion. And so lithium fluoride, if you guys check your solubility rules, Li is a group 1A element. And so you know that when you take lithium fluoride and put it in water, it's going to separate to produce lithium and fluoride ion. And so fluoride ion is present in both of these equations, chemical equations. And so therefore, fluoride is the common ion. And now that we know that fluoride is the common ion, that's going to change how we represent our ice table. And I'll show you that once I built it. Actually, I'm going to see if I can just copy and paste this. I'll just erase some stuff. Oops. Okay. So here we have our ice table to represent strontium fluoride, represent the progress of strontium fluoride dissociating into its ions. And so we know that some amount of strontium fluoride will be soluble. So that's why we say minus S. So we're going to consume some strontium fluoride because some part of it is soluble. And we are going to produce, and that produces strontium and the fluoride ion. Okay. So that much in your ice table does not change. And so if you guys think about this, so we have 0.25 molar of lithium fluoride. And so if you have 0.25 molar of lithium fluoride, when you separate them into 2 pieces, the value that you get is 0.25 molar of lithium and 0.25 molar of fluoride. Now, usually students are just like, wait, what? Why do you have 0.25? When you split it, isn't it just by half? So that's like the common question that I get. And so for those who are familiar with Lego blocks, or you don't even have to do like Lego blocks, let's just say a pen with a cap, right? So if you have a pen and a cap, if you have, let's say, 5, so I'm going to repeat this. I'm going to duplicate this 5 times, maybe just 3, because I just realized how much I have to do this for 5. So let's just say that you have 3 pens with a cap, and that's going to represent the lithium fluoride. Okay. So if you want, you can put in lithium for the pen and the fluoride for the cap. Doesn't really matter. When you separate all the pens from the caps, how many pens do you get? How many caps do you get? Okay. And so if you're not sure, feel free to grab 3 pens with a cap and physically do it. And so the result is that you guys will get 3 pens, which is going to represent lithium, and you also get 3 caps. That represents fluoride. And so if you have a 0.25 molar concentration of lithium fluoride, when it dissolves, it will produce 0.25 molar of lithium and 0.25 molar of fluoride. Okay. And so what this is telling us, if you guys read the problem just a little bit more, so calculate the molar solubility of strontium fluoride in 0.25 molar of lithium fluoride. So there is already lithium fluoride present in the solution. And therefore, there is an initial concentration. And the initial concentration is 0.25, but that's going to be placed under fluoride because that is the common ion between our substance and the substance that's already present in the solution. And so the rest is going to be blanked out, and very similar to what we did, this just cancels out when we apply this to the mass action expression. And so we're going to go ahead and add downwards to get the equilibrium amount. So this is going to be 0.25 plus 2s. All right. And so now that we have our equilibrium expression for each substance, let's go ahead and write that mass action expression where KSP, I think I'll just copy and paste it. Oops. Oops. Okay. All right, so here we have the mass action expression. That mass action expression does not change. Oh wait, why did I do that? I needed that. This I don't need. All right, and so here we're going to place our equilibrium expression for each substance into the mass action expression for the solubility product constant. And that's going to give me S to the first times this by 0.25 plus 2S squared. Okay. Now, if you look at this term that I'm going to highlight, this is 0.25 plus 2s squared. And so this is a binomial. And if you guys are thinking, oh man, okay, does that mean I have to express it twice and then I have to FOIL it, and then since I have an s squared, do I need to use the quadratic equation? And the answer is no. So very similar to all of the equilibrium problems that you guys have done, whether it's acid-base equilibrium or just equilibrium just in general, we can start approximating the change by looking at the magnitude of our equilibrium constant. And so if you guys look at the magnitude of the KSP, it's times 10 to the negative 9. So this is like a rough measure of how much product we're going to produce, if you catch my drift. And so since this is times 10 to the negative 9, it's far, far less than 1. This is telling me that if I have an actual concentration value, such as 0.25, and if I'm comparing it to this change, because this is times 10 to the negative 9, this change is so small that it will not change the value that it's being compared to. And so what I'm getting at is being able to ignore the 2s because the magnitude of the KSP is far, far less than 1. And so what I get is s times 0.25 squared. All right? So it's very similar to all of the other equilibrium problems that you guys have done. The only difference between this and another is the idea that we're not ignoring the x in our denominator. We're ignoring the s, which is the x really, for that's found in the numerator. Okay. So whenever you guys are comparing some type of change to that of an actual value, right? And it's far, far less than 1, you can go ahead and ignore that term. Now you don't want to ignore this term because you're comparing it against nothing, right? So s plus 0, that's a significant change. That's greater than 0. And so anything that's greater than 0, it'll change the number. But if you add in 0.25 times 1 times 10 to the negative 9 or whatever, it's not going to change that value. It's still going to be 0.25. All right. And so we're going to go ahead and just finish this up. So what we're going to do is we are going to square this. And then when we square this, we are going to divide it to the other side. So 0.25 squared is going to be 6.25 times 10 to the negative 2. And so I'm going to divide this by 6.25 times 10 to the negative 2. And so the value for s, so 0.25 squared is 6.25 times 10 to the negative 2. And so if I divide those two values, so 4.33, so 4.33 times 10 to the negative 9, divide this by 6.25 times 10 to the negative 2, I'm going to get 6.93 times 10 to the negative 8. And since I'm just talking about the molar solubility of, so S, remember, is the molar solubility. Of strontium fluoride, my final answer is going to be 6.93 times 10 to the negative 8 molar. Okay. So what I'm going to do is I'm going to copy this portion, and then I'm going to paste it right next to the number. Okay. And so this is the molar solubility of strontium fluoride if 0.25 moles, 0.25 moles per liter of lithium fluoride is present in that solution. And I'm going to go ahead and copy, I'm going to copy the result from our first answer so that we can compare these molar solubilities. And so if you notice, the molar solubility in water is going to be 1.03 times 10 to the negative 3. However, the molar solubility of strontium fluoride in lithium, in this amount of lithium fluoride, decreases. To 6.93 times 10 to the negative 8. Okay. And once again, we can think about this like Le Chatelier's principle, And so if we increase the concentration of fluoride, to counteract this change, the equilibrium will shift to the left. And when you increase the equilibrium, or when you shift the equilibrium to the left, the system is producing more strontium fluorides rather than dissociating it. Okay. So we're able to quantify the change in molar solubility in the presence of a common ion. Okay. All right, so we're going to go ahead and do this last problem here, part C. So we're going to calculate the molar solubility of strontium fluoride in 0.25 molar of strontium phosphate. Oh, actually, you know what? It shouldn't be strontium phosphate. Let's go ahead and do. Okay, so let's just say strontium. So strontium phosphate is an precipitate. Anyways, let's go ahead and do strontium. X. And so whatever this unknown is. And so let's just say SR2 X3. There. Problem solved. And let's just say that this is soluble. Problem solved. Okay. So we're going to calculate the molar solubility of strontium fluoride in 0.25 molar of strontium X, whatever that X is. Doesn't matter. The only thing that matters is that it's completely soluble. And so very similar to what we've done, I'm going to go ahead and just copy some of the ice table and the balanced chemical equation and all of that stuff. So I'm going to copy this. And I'm going to erase some stuff just to kind of reset it for this problem. Okay. And so we're going to determine the molar solubility when strontium fluoride is in 0.25 molar of this guy. And so let's go ahead and take a look at that substance, so SR2X3. And so just imagine that this is aqueous. And so if this is aqueous, it's going to produce 2 moles of strontium. And it's going to produce 3 moles of this anion that we don't know and we don't care about. It's just a spectator ion, so it'll just be aqueous. Okay. And so if you guys are looking at both of these chemical equations, you guys will see that strontium is the common ion between these two equations. Okay. And so if the solution has 0.25 molar concentration of SR2X3, so if we have 0.25 molar concentration of this, when this salt dissolves, it's going to produce 0.25 molar concentration of SR and 0.25 molar concentration of SR. Now, this is where things kind of change a little bit. Notice that the ratio is 2 and 3. So that means that we have to multiply this value, we have to multiply the coefficient to the concentration. And so the true concentration that we have for strontium is going to be 0.50 molar. Okay? And I mean, just for completion, we can say that the X minus is going to have a total concentration of 0.75 molar. Okay? So once again, it's that idea of like the cap, right? However, this time, since there's coefficients, we need to multiply that concentration to it. And so since the common ion is strontium, and if you guys read the question, this strontium fluoride is already in this solution. So there is an initial concentration of strontium, and that's 0.50 molar. And so since there is no common ion for fluoride and there's no initial amount of strontium fluoride, we're going to go ahead and just ignore these two. And we know that some amount of SRF2 is going to be soluble to produce SR2 plus or strontium cation and 2 times S. And so what we're going to do here is we are going to add downwards, so 0.50 plus S, and then plus 2 times S. Okay. And once again, we can go ahead and cross this out because that is a solid, and we do not use, oops. Okay. All right, so we don't really use the solid in the mass action expression. It's volume independent. All right, so what we're going to do is we're going to place these expressions at equilibrium inside the mass action expression. And so this is going to give us KSP is equal to 0.50 plus S raised to the first times this by 2S squared. And we're going to go ahead and plug in our KSP, 4.33 times 10 to the negative 9. And this is going to give us 0.50 plus S to the first times this by 2S squared. Okay. Now, 0.50 is a value, right? So this number is being compared to the change in the ice table, right? So S represents the change in our ice table. And so if you look at the magnitude once again of the KSP, it's times 10 to the negative 9. And so since you're comparing the change that has, a low value to begin with to that of, a larger, much larger value, then it's not going to change this value significantly. And I'm not specifically saying that the change is times 10 to the negative 9. I'm using the magnitude as a tool of evaluation to assess whether or not the change is going to affect the number it's being added to, which is 0.50. And so, long story short, it's not, so therefore you can go ahead and ignore it. So I'm going to go ahead and ignore this S. And I'm still going to keep this 2S because we're not comparing it against another number. It's just 2 times S squared, which was going to give us a value that's greater than 0, and that's significant. And so 4.33 times 10 to the negative 9 equal to 0.50 raised to the first power times this by 4S squared. Okay. And so I'm just going to go ahead and multiply these two. And so this is going to be 2. So 0.50 times 4, that's half of 4, which is 2. So I'm going to take 4.33 times 10 to the negative 9, and then I'm going to divide that by 2. And what I get here is going to be 2.165 times 10 to the negative 9. And I'm going to remind myself to just keep 3 sig figs. And that's going to give me s squared. And so I'm going to square root my answer. And when I square root my answer, the value of s is going to be 4.65 times 10 to the negative 5. And so this is going to represent the molar solubility of strontium fluoride in 0.25 molar concentration of strontium X3. And so I'm going to go ahead and plug in these numbers. So this is going to be 4.65 times 10 to the negative 5 molar. And so, highlight this. Oops. Let's not do strontium phosphate. And so the reason why I crossed out strontium phosphate is because phosphates are typically insoluble. And so let me change that to SR2X3. And I'm going to say that this is aqueous to begin with. So if you guys are looking at these values, remember this is part A is your control, if you will. If you're comparing your control, the calcium, the strontium fluoride that's in water, if you're comparing its molar solubility to that when strontium fluoride is in 0.25 moles, 0.25 molar concentration of SR2X3, notice that there's still a decrease. Now the magnitude of the decrease is not as much compared to fluoride. The reason why is because of this ratio, right? So you're producing, so you have more of the fluorides. And if you have more of the fluorides, and if fluoride is the common ion, it's going to have a greater effect to lowering the molar solubility of strontium fluoride compared to the strontium. Okay? And so this is the reason why we see a difference in value. Like the value doesn't get lower from B. It's lower than A. Between A and C, there's a decrease, and between A and B, there's a decrease as well. And that's the only thing that we can do. The reason why there's a gap, once again, between these two is because of the coefficients. So since the coefficient of fluoride is 2, it would have a greater effect on the molar solubility of strontium fluoride. Okay, and so this is pretty much it for this lecture video. There's just some key techniques that are starkly different from the previous lecture video, and it's this idea of adding the initial concentration. And you'll only do this if you have a common ion, and make sure that you guys are ignoring the change that's being compared to a number if the KSP is far, far less than 1, and typically it is. All right, so that's it for this lecture video. The next lecture video will discuss some more awesome stuff related to the solubility of slightly soluble salts. See you guys.